On June 30, 1908, a colossal explosion ripped through the skies over Siberia, leveling 80 million trees across 2,000 square kilometers. The blast's force was so immense it registered on seismic stations across Europe and created atmospheric pressure waves detectable even in the United Kingdom. This was the Tunguska event, a mystery baffling scientists over a century later. For decades, the leading theory has been an airburst from a meteoroid or comet fragment exploding kilometers above the Earth's surface. But what if the truth lies not in the sky, but hidden beneath the waves? What if the Tunguska-like event of 1908 was caused by a deep-sea impact? The idea seems outlandish at first glance. We often picture cosmic impacts as fiery streaks across the sky, culminating in terrestrial craters or atmospheric detonations. Yet, our planet is 71% ocean. It stands to reason that significant extraterrestrial objects destined for Earth would, in fact, plunge into the vast, watery abyss. When a bolide, an incredibly bright meteor, hits water, it's not simply a splash. The physics are far more complex and terrifying. Imagine a solid object, perhaps tens of meters across, slamming into the ocean at tens of thousands of kilometers per hour. The initial impact would create a colossal cavity, instantly vaporizing immense quantities of water, generating superheated steam erupting skyward with unimaginable force. This isn't just a big wave, this is a cataclysmic energy transfer. The object decelerates almost instantly, converting its kinetic energy into heat, sound, and a massive pressure wave that travels both through the water and into the atmosphere above. The water itself acts as a massive shock absorber, but also as a conduit for destructive energy, potentially triggering tsunamis that could devastate distant coastlines, depending on impact location and depth. The vaporized water, heated to extreme temperatures, would create an immense plume, potentially mimicking an atmospheric explosion even if the object itself plunged deep beneath the surface. So, if such an event occurred, what evidence would remain, especially if it happened over a century ago in the deep ocean? This is where the mystery deepens. Unlike a land impact, there's no visible crater, no shattered rock formations to analyze directly. The ocean floor is dynamic, ever-changing, constantly being covered by sediment, scoured by currents, and altered by tectonic activity. Any direct evidence from the impact itself, fragments of the bolide, distinct impact structures, would be incredibly difficult to locate. We'd be looking for subtle signatures, seismic anomalies, perhaps a unique layering of sediment containing extraterrestrial material like microtectites, tiny glassy spheres formed from molten rock ejected during an impact. But finding these in the vast, unexplored expanses of the deep sea is like searching for a specific grain of sand on every beach in the world. Oceanographic surveys are expensive and time-consuming, and even with modern technology, charting every inch of the seafloor is a monumental task, let alone pinpointing an ancient, hidden impact site. Let's reconsider the 1908 Tunguska event through this deep-sea lens. One of the most puzzling aspects of Tunguska is the lack of an impact crater. While the airburst theory explains this by positing the object disintegrated before hitting the ground, a deep-sea impact offers an alternative. An object plunging into the ocean would not create a land crater. Furthermore, the immense atmospheric pressure wave and heat pulse generated by a deep-sea impact steam plume could easily account for the flattened forests and observed atmospheric phenomena. The unique light nights reported across Europe in the aftermath, attributed to dust and ice particles high in the atmosphere, could also align with a massive injection of water vapor and particulate matter from an oceanic explosion. There's also the question of the object's composition. If it were a stony asteroid, it might survive an atmospheric journey to impact land. But if it were a fragile comet fragment, rich in ice and volatiles, a deep-sea impact might be even more likely, as it would be less likely to survive an atmospheric journey intact for a land impact, yet still possess enough mass and velocity to create a devastating oceanic event. Could the specific seismic signatures and atmospheric pressure waves recorded in 1908 hint at a deep-sea origin rather than a purely aerial one? It's a question that challenges our long-held assumptions. While a deep-sea impact for Tunguska remains a hypothesis, it's important to recognize that deep-sea impacts are not theoretical impossibilities. Earth's geological record, though often obscured, offers glimpses of such events. Scientists have, on rare occasions, discovered layers of microtectites in deep-sea sediment cores that suggest ancient oceanic impacts. These tiny glass beads, formed from molten rock, are ejected at extreme velocities during an impact and can settle across vast areas of the ocean floor. While no specific bolide has been definitively linked to these deep-sea tektite fields, their presence confirms that cosmic objects do indeed strike our oceans, often leaving behind only the most subtle of clues. Imagine the sheer number of smaller objects that hit our oceans annually, going completely unnoticed by humanity, their energy dissipated or absorbed by the vast water column. These events, though perhaps not on the scale of Tunguska, are a constant reminder of our planet's cosmic vulnerability, and the ocean's role as both a shield and a canvas for these hidden catastrophes. Why does this matter? Exploring the deep-sea impact hypothesis for events like Tunguska isn't just an academic exercise, it has profound implications for our understanding of Earth's history, the deep ocean, and planetary defense. Firstly, it expands our perception of cosmic threats. If a deep-sea impact can mimic an airburst so closely, our detection and analysis methods for future events need to account for this possibility. How would we differentiate between an atmospheric explosion and a major oceanic strike? The seismic and acoustic signatures could be subtly different, requiring more sophisticated monitoring systems. Secondly, it highlights the deep ocean as an unsung arena for cosmic events. The mysteries hidden beneath the waves are not just biological or geological, they are also astronomical. Understanding how these impacts affect marine ecosystems, generate tsunamis, and distribute materials could unlock new insights into oceanography and paleoclimatology. Finally, it reminds us that our planet is constantly bombarded, and the deep ocean, often seen as a silent, unchanging realm, is in fact a dynamic witness to Earth's cosmic journey. Every ripple, every current, every layer of sediment could hold clues to cataclysms we can barely imagine. So, the next time you look out at the vast, enigmatic ocean, consider the secrets it holds, perhaps even the true explanation for one of history's greatest cosmic puzzles. The deep sea is a frontier not just for life, but for understanding the very forces that shape our world. What other hidden impacts await discovery? The answers, as always, lie in the depths. If you found this journey into the unknown intriguing, please give us a like, subscribe for more deep ocean mysteries, and share your own theories in the comments below. Until next time, keep exploring the unseen.